Hi, I'm Andreas Talco, and I'm going to be talking about the hippocampus, which is this region in the brain here in the middle temporal lobes. And of course, like everybody who is interested in neuroscience knows the hippocampus because it's literally the seat of memory, the place where the engram begins for every single event we remember. There is also other stuff that make the hippocampus quite interesting. For instance, it's one of the regions that show the greatest differences in volume and size across individuals. And these differences are magnified across clinically relevant groups. For instance, individuals suffering from certain mental or neurological disorders show abnormally large or small hippocampi, and this is pretty significant. And finally, these differences, at least in part, are driven by a person's experience and everyday life and choices and what they need to do to remember. However, most of these effects, most of these differences across individuals, across groups, and driven by experience, turn out not to actually affect significantly memory function. So the hippocampus does, perform most of the memory functions that we think of. However, for instance, post-traumatic stress disorder and major depression disorder are significantly associated with big reductions in the hippocampal volume, up to 10%, and they do not impact memory function. At the same time, taxi cab drivers in London, for instance, have much larger hippocampi than the normal population or bus drivers in London, but they do not exhibit superior memory. So one way to make sense of this, and this has been theorized before, is that the hippocampus volume grows or shrinks to basically accommodate different demands of memory function. So the more you need to memorize, the more you need cells and synapses, and the more your hippocampus has to grow. While instead, if you don't need to memorize as many things, you actually can shed some synapses and neurons without losing function. And in fact, in 2021, my team and I actually produced a model that was based on this principle and formalized it using information theory. Now, since this model is kind of like the starting point of this talk, I want to go a little bit over this idea. So in this model, the idea is that the neural footprint of a memory, the amount of neurons and synapses that a memory uses, is proportional to its information content, which is in information theory defined as the negative log of the probability that a memory will be used. Now, this is actually, you might have heard of the same principle called representation of free energy in Carl Friston's work, or predictive coding in Rajesh Rao work, but the ideas are pretty much the same. And the other interesting application of this is that if you calculate the mean amount of neural resources across all memories, you get something that is called information entropy. And information entropy is defined like this, and is actually analogous to entropy in a physical system. Now, Smith and al. In 2021 put forward the idea that you can use like a formal model of memory, in this case we use ACTAR, to simulate changes due, for instance, PTSD or major depression, by simulating how memory changes when you have intrusive memories or obsessive thoughts that you keep going over and over, and how these thoughts end up changing the landscape of activation. And by doing this, they end up having an effect on information content and the entropy. In this case, this is the expression of activation of a memory in ACTAR, the sum of decaying traces, and it can be directly connected to the information content of a memory by this equation. And if you calculate the amount of entropy that happens when a memory takes over and becomes much more common than all the other memories, you can predict the amount of change in hippocampus volume. In this case, we were able to actually show the correlation that is vastly reported in the literature and explain why the more frequent is a traumatic memory, the bigger is the reduction in hippocampus volume in patients. The problem with this approach is that no matter how elegant it is or it might seem, it's pretty much a theoretical approach. There is no biological mechanism that was provided for this particular model. And among the problems that are corollary of this is that we had no idea how the hippocampus could form memories right away, create an engram the first time it encounters a memory, but not know in advance the frequency or the activation of the memory, and therefore its neural footprint. The other thing that was troubling to us is that, yes, the model does a good job of explaining some findings, but in fact, the relationship between hippocampus size and volume and memory function is a bit more complex. And I'm going to focus here in this talk on these two other cases. The cases of autism spectrum disorder, ASD, in which the hippocampus is notably larger, but there is not an accompanying better memory function. In fact, memory, if anything, could be possibly worse. And the case we're all familiar with dementia, like Alzheimer's and frontotemporal degeneration, in which the hippocampus is smaller by about the same amount as it is smaller in PTSD, but this decrease in hippocampus volume, in this case, is actually accompanied by a severe diminishment in memory function. So to explain these findings, we decided to move away from the mathematical description of memory in NECTAR and instead get our hands dirty with a biological model, in this case, a neural network model. And this network was trained to encode and retrieve memories of different frequency, much like the hippocampus would need to do. And once we developed this model and trained it, we examined its behavior to test whether A, it would produce efficient coding spontaneously, and B, could explain the findings that we're seeing. Now, to explain the network, I need to go back to the hippocampus and explain a little bit of its physiology. Now, I'm going to zoom in on the hippocampus. Here we have a close-up. And, the circuit of the hippocampus is essentially made by these three regions here in red and yellow. CA3, which is what we think of when we think of the hippocampus, the seat of the engram, and an input region, the dental gyrus, and an output region out of the hippocampus, CA1. The hippocampus is also surrounded by the entorhinal cortex, and all the cortex has to pass to the entorhinal cortex to connect to the hippocampus. In this case, I'm going to take take into account a particular part of the brain, which is the temporal cortex, that contains the visual representation of objects. And I picked this because its connectivity is very well known. In particular, we know that during encoding, information goes from the temporal cortex to the entorhinal, to the dentate, to CA3. In CA3, the engram is made, and during recall, information flows in the opposite direction, going to CA1, then to the entorhinal cortex, and back to the original temporal cortex to re-experience and recreate the original information. Now, this circuit forms a loop, and a loop is typically a problem because it makes neural networks a little bit difficult to train. So the classical trick in this case is to unroll the network and create a network that has basically a temporal cortex at the beginning of the end of the structure of the hierarchy. When you unroll it, you end up with a network that has a large temporal cortex at the end, and a bottleneck at the center, which is CA3. Besides this network is exactly like a feed-forward network. It's not a loop anymore, and this makes it really easy to train for us. This particular network architecture, in fact, is known as the autoencoder, and is designed to actually solve the problem that the hippocampus does, to encode and decode stimuli efficiently, finding an ideal representation of the information here in the middle of the structure. In this particular case, we created this network with the amount of units designed here. It had about 1.4 million parameters, and it was trained with a set of images presented as 28 by 28 matrices of pixels. The images that we used were from the Fashion MNIS database, and since we are dealing with like memory for visual objects, we thought that this was actually a particularly ideal choice. These are pictures, black and white pictures of clothing items of different category, different variety, and different complexity. So pretty much ideal for this type of network analysis. The network was trained using stochastic gradient descent. The most interesting thing was actually the loss function that we used to train the network. And it was designed to capture the biological constraints we had hypothesized. So the loss function in this case contains two penalties. One is the accuracy penalty, the recall error, the difference between the predicted and the actual activation of the upper neurons. This is exactly what we would use as an error in backpropagation, for instance. And the other part of the penalty was what we call the resource penalty. In essence, this is the sum of all the active neurons in the CA3 region of the hippocampus. So every time the hippocampus is using an additional neuron to represent a particular object, a particular stimulus, is actually paying a price. We set this parameter to this value, which is really small because higher parameters tend to make the network unstable. And for smaller parameters, really, we don't see much of a difference. Now, we also created a bias training set where different objects were repeated at different frequency because we wanted to drive differences in information content, which depends, of course, on the log of the probability of a particular memory. So we sampled about 1,000 stimuli, and we divided into a training set so that one stimulus were repeated 1,000 times, 10 were repeated 100 times, 110 times, and 1,000 stimuli were repeated only once. The total was always 4,000 stimuli. Now I'm going to show you a particular representation. I'm going to get back multiple times. In this representation, the different columns represent objects that are repeated at different frequency. Object representing only once here, the object representing 1,000 times here. And this is the part on the top. The on the top represents the image as it was presented to the network at the beginning of the autoencoder part, while the part at the bottom represents the object as it was recalled by the decoder part of the network. The part in the middle is the internal representation of each of these objects at the level of CA3. And you can see that spontaneously this model is compressing information so that more frequent objects pretty much can just use a grandmother set type of representation, while less frequent objects have a very sparse representation. In fact, if we look at the average changes, you see that there is a strong effect of stimulus frequency on the number of neurons that are used to represent the memory at the level of CA3. And to make the thing more clear, this amount of compression pretty much matches the theoretical predictions based on information content. This is the negative log of the probability of a memory, and this is the compounding number of neurons for that memory. Can we also explain the role of experience? To test this, we actually repeated the same test, but this time we created a set of 4,000 objects in which the same items were repeated pretty much the same amount of times, only 3 or 4 times. This is an unbiased training set in which every item has the same information content. And as expected, having the same information content doesn't drive reduction in the information representation. All the items actually have the same amount of neurons used for representing them. Now, we want to deal now with the cases we've seen before, ASD and dementia. In the case of ASD, the abnormality seen in the hippocampus is actually a larger hippocampus. And we reason that this could be connected to our lambda parameter. One of the characteristics of ASD is that individuals having this disorder tend to exhibit much, much less GABA receptor and synapses in the brain than healthy controls, up to 40% less. And of course, inhibitory GABAergic synapses in the brain are mostly used for lateral inhibition, which is actually one of the mechanisms by which sparseness is induced. So it's pretty much the same functional system of our lambda penalty. So in order to test this idea, we actually ran a simulation which will set the penalty back to 0. We trained with the original bias data set with one stimulus represented 1,000 times, another stimuli for an increasing amount of times. And this time we got this effect here shown in green. In practice, with the lambda penalty set to 0, the model cannot take advantage of lateral inhibition or penalty to specify representations. All the models are given pretty much, all the stimuli are given pretty much the same amount of neurons, allocated the same amount of resources, independent of the frequency. In fact, they are allocated more resources than they would be under normal condition, which might be an explanation for why the hippocampus is larger in ASD. Finally, we want to look at the effect of dementia, and of course, the effects of dementia are easily captured by literally suppressing a certain amount of neurons in the representation after learning is induced. And we can see that whether we count the recall error or the correlation between the recall item and the original object that was encoded, we see a huge effect of the number of neurons that were actually removed from the representation on the quality of the remembered past. Interesting enough, we can also capture another. In ASD, the risk of dementia, the prevalence of dementia is 4 times higher as normal population. And we reason the sparser cause, like grandmother says, can provide a form of resistance against dementia neuronal loss. In practice, it's harder to lose a memory if it's only represented by a single neuron. So in order to do this, we run simulations again, we divide again the parameter of neural integrity, and you can see that for all the different levels of stimulus frequency, the non-sparse model that represents ASD has a lower performance in the recall than the sparse model that we have originally seen, showing case that, the resilience to dementia is higher in the population that does not have ASD. So in summary, we're seeing a model that is an autoencoded model of the hippocampus. It can naturally produce efficient coding, and this matches with the idea of information entropy, free energy, and predictive coding. It also explains changes in hippocampus volume that are due to experience in PTSD, like the theoretical model of Smith et al., but also ASD, which is a new finding, and dementia, which is a new finding, and interaction between the two. This is it. I would like to thank my incredible team. And if anybody is interested in comments, suggestions, please send us an email. And also please check out our repository with our code.